Thank you very much for a nice introduction. And I'd like to thank the organizers for providing the opportunity to speak on this subject and also arranging a very nice workshop. I apologize that I'm not able to visit in person for various limitations, but at some time I'd like to really visit Bangalore. So the title of my talk is about multipoles. So, by the way, I was retired from ISSP Tokyo University last March, so I now have a visiting position at these two institutes, but I still keep activities at ISSP. So what I'm going to tell you today is mostly done in ISSP. So outline, as an introduction, first I talk about briefly about the multipoles in localized electron system, how to detect by NMR. But my main topics today is the itinerant system, which is a cadmium, rhenium, oxygen, pyrophore metal, which shows a very interesting parity-breaking phase transitions. And I present our recent cadmium night shift data, and especially I will discuss the new method of representation analysis of the NMR shift data to identify symmetries of order parameters. And finally, I will summarize and state our outlook. So, and this work has been done in collaboration with these people, Daigoro Hirai and Zenji Hiroi. Has discovered this material and also developed a very nice high-quality single crystals. Hirai-san has now recently moved to Nagoya University. Nobuyoshi Mera was my former master student, and I'd like to especially thank Takumi Hasegawa sensei from Hiroshima University. He's a specialist on the Raman spectroscopy, and he developed essentially all the new methods of analyzing symmetry of NMR night shift data. Okay, so before going into the main topics, I briefly tell you the early effort of detecting multiple order by NMR. So the concept of multipole has been developed mostly in FA electron materials, where large degeneracy of the FA electron ground state can be described by various degrees of freedom, include not only the magnetic dipole, but electric quadrupole or magnetic octupole. And probably most well-known example is the selenium hexaboride, where the selenium 3+ has a gamma 8 quartet ground state. So it has various type of quadrupole and octupole degree of freedom, in addition to magnetic dipole. And early on, I did an NMR experiment a long time ago. Actually, this is my thesis work. But and then at that time, this kind of phase diagram has been known. So people looked at the two ordered phases, and this phase 2, which occupy a very broad area in field and temperature plane, is believed to be antiferro-octupole order. And when I did the NMR experiment, I found the NMR line splitting going into this phase 2 from paramagnetic phase. And this is angular dependence of the line splitting at these 3 boron sites, 1, 2, 3, as a function of angle. And when you apply a magnetic field along Z direction, we found that these boron 3 shows the line splitting. So at that time, I thought this is probably field-induced antiferromagnetic ordering on top of the quadrupole order. But if this line splitting, if you like to explain this line splitting by the antiferromagnetic dipole moment, the ordering wave vector must be 001 half, something like that. However, the neutron scattering experiment at the same time did not find any such ordered wave vector. In fact, for the field around 001, there's no black peak in neutron scattering. And this inconsistency remains a mystery for a long time. And this problem was solved really 14 years later by these people. And they proposed that what the NMR line splitting is not seeing the dipole order of dipole moment, but orders of octupole moment. And the reason is that if you write down the symmetry around interaction between the boron nuclei and cerium multiple moment, the transformation property is different for dipole moment and octupole moment. This Tx by Z is the octupole moment defined in this way, where the upper bar means cyclic permutation of all the variables. Now, the essential point is that when I rotate the crystal about 90 degrees along C-axis, this cerium one side moves to cerium 2 and 3, 4. And then at the same time, the dipole moment does not change because Z component of dipole moment is invariant under pi over 2 rotation. However, the octupole moment changes sign by pi over 2 rotation. So this is why the this simple Nair type order of octupole moment produce a finite hyperfine field at the boron site. And this finally resolved an inconsistency with Newton result and NMR, because the Newton see the dipole field-induced dipole moment, quadrupole moment of 1/2 and 1/2 in this compound. And physically, this is quite natural because there's octupole, antiferro-octupole order of OX5 quadrupole. That means there is a charge distribution is something like that. So here the white area is a charge rich region, and dark area shows a charge poor region. And this boron nuclei is closer to the charge poor region, while this white upper boron site is close to the charge rich region. So then it is natural that if you apply magnetic field, the spin density induced on this cerium site has a staggered moment. So and actually this is nothing but the field-induced octupole moment like that. So the lesson we can learn from this is NMR is a really powerful local probe to look at the multiple moment once we know exactly the symmetry properties of the materials. But since then, the concept of multiple moment is generalized to not only to localized electrons, but also to itinerant electrons. And this is a recent work by Hayami-san and the collaborator, which try to generalize the concept of multiple to cover all electronic degree of freedom. So in not only the electric dipole, electric multiple and magnetic multiple, they introduce electric toroidal or magnetic toroidal moment, which cover the all combination of transformation property with respect to parity and time reversal symmetry. So this is quite a strong driving force to look into the various novel phases in itinerant system, especially with strong spin-orbit coupling. So let me now move to the main topics of cadmium, uranium, and oxygen. And this pyrocolor metal has been discovered a long time ago. And around 2000, the two groups, one by Hiroi at ISSP and the other by Yoshimura-san at Kyoto University, found that this material actually becomes superconducting below about 1 Kelvin. And also they found a peculiar cascade of transition at these two temperatures. So this is a resistivity versus temperature, and there's the resistivity shows the sudden drops at around 200 K, and some step at 120 K. Then this is a sustainability and also the cadmium night shift, which we did a long time ago. And they show at this upper transition TS1, the rapid decrease of sustainability, indicating a significant reduction of the density of state. Although there's not much change at TS2 in the magnetic sustainability. The people in early days, people looked into the structure change by X-ray diffraction, and it has been recognized that the phases. And from now on, we call this is phase 1, and this is phase 2, and this is phase 3. And although in phase 1, the materials maintain cubic bipolar FT3/M structure, people recognize that the low temperature phases lose inversion symmetry because some forbidden reflection clearly observed at low temperature. And also, they suspect change of symmetry from cubic to tetragonal at low temperature, but atomic displacement or tetragonal distinction was very, very small, so they could not really make a refinement of atomic position. But Yamauchi-san at that time collected various information from various diffraction techniques, and then finally they concluded this kind of low temperature structures. So the phase 2 is proposed to be this I4/M2 structure with 2 mirrors, and then the phase 3 is another tetragonal structure I4/1-2. And this is a group-subgroup relation. So in the transition at TS1 is a continuous from high symmetry to low symmetry, but the transition at TS2 does not respect group-subgroup symmetry relation. So it must be a first-order transition. And then from this structural information, Serginenko and Kruno came up with a simple random theory, taking the order parameter, which is most probable order parameter is EU type representation coming from these 2 structures. And the simple displacement of this type, EU type displacement are actually compatible. This component is compatible with this structure, and this component is compatible with this structure. And then, so then that they propose that this kind of atomic displacement, which are naturally consistent with a low temperature structure. And since then, there has been not much progress since then, but then the recent revival is brought by 2 remarkable works. One is a theoretical proposal made by Liang Fu, who looked into the possibility of spontaneous parity-breaking ordering. By the way, so since the structure change is very small, so people believe that the transition must be driven by electronic instability. And so Liang Fu proposed one such mechanism coming from strong spin-orbit coupling. So he looked at the materials which has a strong spin-orbit coupling, but maintain the inversion symmetry. And there, because of spin-orbit coupling, the spin-spin interaction can depend on the momentum of electrons and the wave number of electrons, and the various types of high rank interaction can be expected. And so electronic interaction may cause instability or ordering of these spin-orbit coupled observed physical quantities. But since these are parity odd, so if such kind of the ordering takes place for such kind of order with this kind of order parameters, the system must break inversion symmetry. So there is a possibility that electronic systems spontaneously break inversion symmetry to stabilize this kind of exotic ordered state. And actually, he proposed that this multipolar order could be realized in cadmium oxygen 7. And a subsequent work also proposed that the superconducting transition can be enhanced near the quantum critical point where such inversion breaking order can be suppressed to 0 temperature. And actually, the remarkable pressure effect was reported by Kobayashi-san in 2010. And when they applied the pressure, it seems that the parity breaking transition is suppressed to low temperature. And when near the quantum critical point, which is located around 4 gigapascal, the superconducting transition temperature enhanced to 2K. And here the upper critical field is very much enhanced. So, so this sort of motivated many many people to look into these materials again. Also, there is this is a work I mentioned earlier, but theoretical proposal of generalized concept of multipoles by Hymes and company applied their theory to these materials and proposed that the most likely order parameter in phase 2 and phase 3 is the order parity order of electric toroidal quadrupole moment, which has this kind of symmetry. Now, so there are a lot of recent experiments which try to identify the electronic order parameter in these materials. And there are many of them, but I just mentioned representative one example, which is rotation. Let's see, rotational. What is, I forgot. This is a second harmonic generation experiment, but which looks at the rotational anisotropy of the response. So this is so they looked at the anisotropy. They looked into the 111 crystal surface and looked into the anisotropy of reflected second order harmonics light. So and then since this SHG is only possible when the inversion symmetry is broken. So this is a very nice probe to look into the order parameter symmetry of electronic system. But the complication is that there is a very contribution from surface processes, because there is no inversion symmetry in surface. So there are a lot of SHG signal from surface. So one has to distinguish surface contribution from bulk contribution. So, but in the end, they concluded that they found a EU component, which is shown here, which is has a mirror symmetry along 110 plane. But also there is another component with T2U symmetry, and these two components has to coexist to explain the asymmetry of the data. But the strange situation is that although the EU signal is much stronger, shown here, this EU is much stronger than T2U signal, but this behaves like a secondary order parameter, which goes linearly to TC. In contrast to the T2U signal, which is much weaker but has a temperature dependence compatible with a primary order parameter. So the situation is quite controversial. So this motivated us to look into the cadmium NMR once again. So now during the course of 20 years, the quality of crystal has been improved quite tremendously. So so we have a very narrow cadmium line with shown here. So in phase 1, we looked into the angular dependence of Knight shift when the field is rotated in 110 plane. And in phase 1, everything is just as expected, and we see a uniaxial angular dependence of Knight shift. There are 4 cadmium sites in unit cell, and since the field is in the mirror plane, the signal from site 2 and site 3 coincide. So this is just what we should expect for that threefold symmetric site of cadmium site, and this can be fit with this uniaxial expression where the chi parallel, which is correspond to here, and chi perpendicular, which correspond to these 2 points, is the principal value of the Knight shift tensor. Now when we go into the low temperature phase, the line splitting occurs. So at 130 K, which is in phase 2, the line split along 110 axis, and the 2 lines always appears, which merges at 110. So this splitting, the intensive ratio is approximately 2 to 1. So it looks pretty much caused by domain of 3 domains, because once you have a tetragonal phase, you would expect 3 tetragonal domains. So this splitting seems compatible with this domain coexistence. However, if you further go into the lower temperature phase 3, then this line with red line further split into 2. So we have in total 7 lines. Now we could just fit this to conventional cosine square theta type function and determine the direction of principal value and the principal axis for each of these sides. But this probably doesn't tell anything about the nature or physics of the system. So we clearly need some guiding principle to understand what this data means. So and then Takigawa-san came up with a very nice idea of using performing representation analysis for the night shift measurement. So I'll explain this step by step. But so first, the cadmium has a point symmetry of 3 by m. So the first thing we should do is construct a basis of irreducible representation of this point group from the 9 component of the shift tensor at cadmium side. What we measure is the shift tensor is defined like this. So if you apply external field, the electronic system produces a magnetic hyperfine field which acts on the nuclear spin. So the night shift tensor represents the electronic response to the magnetic field, and what we measure as a night shift is a component of this shift tensor along the direction of external field. So this decomposition is quite easy. We can do just by inspection. If I consider the transformation properties of component of a nuclear spin and magnetic field. And the result is that we have two totally symmetric combination here. That's isotropic part, and this is this one is threefold symmetry in the actual part, with both of which is compatible with this 3D point symmetry of the cadmium site. And so this is what we expect in phase 1. In addition to that, there are other components which is not totally it's not invariant under the point symmetry of cadmium site, but form a higher dimensional representation. And that there are two easy representation. One is a pair of these two, and the other is a pair of these two. And it turned out these two components are actually explain the experimental observation of in phase 2 and phase 3 data. And then actually, I have shown here only the symmetric tensor, but actually there are anti-symmetric tensors that are shown here. And this is actually allowed, but actually it has a quite interesting effect, especially in the chiral crystals. But since the hyperfine field produced by anti-symmetric tensors actually perpendicular to the external field, so it does not contribute to the night shift in paramagnetic material. So we cannot detect such component. So we only consider the symmetric part. The next we will so far I looked at only the one cadmium site. And then there are 4 cadmium sites, so we have to consider the shift tensor at other cadmium sites. And these other cadmium sites can be obtained by C2 rotation applied to cadmium 1 site. For example, cadmium 2 sites can be obtained by C2 along X, and cadmium 3 along Y, and so forth. So therefore, if I write the general night shift tensor in this way, then the night shift tensor at other sites can be easily obtained, something like that. And finally, we have to consider the domain, 3 domains in tetragonal phase. this will further bring the NMR line splitting. And so instead of considering 3 domains, it's more easy to consider that the different orientation of field for different domain. So for example, for domain 2, we see axis along X is equivalent to the field rotated in the YZ plane in domain 1. So, and then finally, then we can express the angle dependence of night shift by 6 parameters, the basis of the night shift tensor for 12 NMR lines. That is 4 sites in unit cell and 3 domains. And then this is what we did. So in phase 1, as we expect, we only have a totally symmetric component, finite. In phase 2, we have one of the P2G AG component of C1 component appears. That brings this splitting with 3 domains. In phase 3, we find that in addition to the C1 component, another AG component, B1, also becomes finite. And this means actually the order parameter rotate in the 2-dimensional AG space. And I would come back to this later on. Now let's look at the temperature dependence of each component. So A1Z components are the temperature dependence, which is very similar to just magnetic susceptibility. And there is a clear kink at 203 Kelvin, which is here. And the uniaxial component also shows a similar kink at 200 K, although accuracy is not as good as A1 component. Now, and then we at this at the phase TS1, we saw a splitting of line, which is expressed by C1 component, and it looks as if this transition temperature could be slightly different from the transition temperature of C1, where if we fit it to some power of fitting, because this is differ by 1.5 dB. So there is a possibility that the transition at TS1 is not a single transition, but a double transition go through so this first step is just a breaking of inversion symmetry, and then the second step is symmetry lowering from cubic to tetragonal. So I looked at the different crystals very carefully. What I found is that the kink at A component, which is again 203K, but the splitting at this temperature range, it's very hard to distinguish a single peak between 2 peaks. And if we consider this C1 is a secondary order parameter, which has a linear T dependence near the critical temperature, then the critical temperature is within the experimental resolution is the same. So it seems that within the experimental resolution, the single transition occurs, breaking inversion and cubic rotational symmetry simultaneously. Now, so far, we looked at only the symmetry of the cadmium site, but what we really want to know is the order parameter of the whole crystal, which has a symmetry group of OH. So how can we get information of the whole crystal out of the local measurement and cadmium site? This is again Hasegawa-san gave us a very clear idea using the so-called induced representation of OH group. Since this symmetry group of cadmium site is a subgroup of the crystal symmetry, we can make a so-called coset decomposition. And these 4 operations is actually nothing but what transforms 4 cadmium sites within each other. So as I mentioned earlier, C2X brings the cadmium 1 site into cadmium 2, but this doesn't change the component of the night shift, because this does not change with C2 rotation. So if we correct all these night shift tensor at 4 sites, we obtain the totally symmetric representation for the whole OH group. However, we could make different bases which with side change and which are orthogonal to these bases. And there are three of them which correspond to X, Y, Z component of the T2G representation of OH. So that means from A1G component of the cadmium size symmetry, we can get A1G and T2G representation of the crystal symmetry group. The same thing can be done for EG component, and it turned out we have so if we just correct the EG component for cadmium site, then this will bring us EG representation of the crystal. But however, in addition to that, we can get T1G and T2G representation of the crystal out of the EG component of the cadmium size symmetry. And this is the same situation applies for the one other EG representation, which is expressed by D component. So now we understand that out of the K tensor of 4 cadmium sites, that can generate 2 A1G and 2 EG and 2 T1G and 4 T2G. In addition, in total, 10 different representations of a crystal group. So what we should do, so we already know that the two easy representation give a very nice reproduction of the experimental data. So what we should do is, if there's any other combination or any other representation can give equally good fit to our experimental data. So I checked all of them. I just show a representative example. So these are the example of T2G representation, and none of them gives similar line splitting pattern. And these are the T1G representation. Again, both of these are completely different from what we observed experimentally. So now we can conclude quite firmly that experimental results can be reproduced only by EG component of the OH, the crystal group, which are, but however, a secondary order parameter of the primary EU order. Unfortunately, the cadmium NMR does not have direct access to the EU order parameter. So finally, I briefly mentioned that the very strange behavior of the phase transition at TS2, which was believed to be first order, but actually it turned out it's a continuous cascade transition with a new intermediate phase. So when I looked at this line, which is split in phase 2, very carefully, we found that the one of these lines, which is twice as strong as the other one, tends to start to split at around 130 K. And then in this temperature range, there are 3 peaks here. And then this line then is merging to the low frequency side. And finally, at 100 K, we recover the 2-peak structure. This is now the spectrum of phase 3. So in the intermediate phase, the angular dependency looks like that. And that can be fit to the combination of these C1 and C2 component with both of, so each of these correspond to the 2-dimensional EG representation. So this means in this intermediate temperature range, order parameter is rotating in the 2-dimensional order parameter space. So it's probably, and then this naturally make good connection to the EU order parameter, which is proposed long time ago. So as far as I discussed earlier, in early times, these people proposed EU order parameter and discussed the Landau theory, and this naturally compatible with the proposed space group in phase 2 and phase 3. So these two are the EU order parameter, which is compatible with phase. This is phase 2 and this is phase 3. And it's convenient to write down, make a diagram of two-dimensional order parameter space, eta 1 and eta 2. And the switching from here to here correspond to 30-degree rotation from here to here. Now, what we observed by NMR is a rotation of easy parameter space, C1, C2 component. And so this is experiment from the value experimental value of C1 and C2. We can determine the phase angle along this intermediate phase. And what happens is we start from 0 degree. It tends to approach a 60 degree. So it's a 60 degree rotation. So the 0 degree corresponds to the phase 2 structure, and 6 degree corresponds to phase 3 structure. And this is quite natural because this is a secondary order parameter. So it's proportional to the square of EU order parameter. So this is quite naturally understood that we, in this easy parameter space, this continuous change corresponds to a 60-degree rotation. Now if we look at this carefully, the angle doesn't really reach to 60 degree completely. So, and it is still possible, although this peak looks a single peak, it's still possible, but the margin is quite not complete. And so the system may be stopping at some angle here and continue to be orthorhombic down to low temperature. This is, we cannot distinguish this with our experimental resolution. But this sequence of transition is quite strange because the symmetry, crystal symmetry changes from tetragonal to orthorhombic at this temperature, but then symmetry is increased to tetragonal again in this temperature. And this is shows a very a heavy degeneracy of free energy in this order parameter space. Now, the one final thing that which we do not quite understand is that this D1 component appears only in phase 3. And at the same time, the C1 component, actually this is the amplitude of two-dimensional component, but decrease when when entering into the phase 3. Since these two components have the same symmetry, so there is no apparent distinction between these two. So it's quite strange that there seems to be some compensation, what some rule is working on over the two components, and there must be some physics behind this, but we do not understand at this point. So let me summarize. So first of all, I'd like to emphasize that angle resolved NMR, that means the very precise angular dependence of physical quantity, NMR quantity for single crystal sample, combined with a representation analysis, provide a very powerful technique to identify complex order of correlated electron systems. And cadmium radium oxide is a very challenging playground to explore novel behavior of spin-orbit coupled metals, especially in high pressure, then some exotic superconductivity could be expected. And also, since cadmium NMR does not allow direct access to the auto parity order parameter, we are now starting oxygen NMR, because oxygen is not located in the central symmetric position. So the parity breaking will split the oxygen site into double the number of oxygen lines. So this will be a more direct probe for parity violation or parity fluctuation. So thank you very much for your attention.
Thank you very much. Okay, so this talk is open for discussion. We have time for short questions. Please.
Thank you very much. I have a quick two questions. One is that how much, I mean, you presented the evidence for different order parameters coming from NMR. How much can be deduced from other experiments like X-ray? Is there any magnetostriction or any?
Well, there are many experiments done, but here in this analysis, I just consider NMR, only NMR spectra.
Okay. And the second question is that when you show your diagrams, then very often you see that like many lines go into a single point. I mean, there's a huge
Oh,
degeneracy.
yes.
Is there any simple physical explanation why this happens?
Let me see. You mean that this simulation?
Yes, yes.
Yes. Well, actually, that depends on the component. So these are both C3 is one T1G component. So I don't know. It just happened to be that combination. But so in terms of symmetry, there's no distinction for symmetry. But it just so in general field direction, the number of lines are probably the same. But here, because this is here. So for example, this D component sorry, is more coming only from the off diagonal terms. Sorry. So when you look at this component, these are only off diagonal component, but C component is diagonal. So that's the reason why you do not see a splitting along 001 axis. Right. So this is clearly yeah. So it's clear that the only diagonal component and this has only off diagonal component. So that's the reason why the splitting pattern is different. Is that
Okay. Okay, thank you very much.
But the symmetry is the same. So I think there's no reason to expect one of them appears in particular phase.
Okay, thank you very much. So we are running out of time. Let's thank Takigawa Sensei once more.
Okay, thank you very much.